Every quantum physics principle explained. Wave-particle duality. You've probably thrown a ball before. Normally, you'd think of the ball as a solid object moving through space. But in the quantum world, that ball can also behave like a wave, similar to ripples in a pond. This is wave-particle duality. It means that tiny things like electrons or photons, particles of light, can act like both particles and waves. When we're not looking at them, they spread out like waves. But when we try to measure or observe them, they suddenly act like particles with a specific location. It's as if you threw a ball and it spread out like a wave until it hit something, then suddenly became a solid ball again. Weird, right? But that's how things work in the quantum world. The uncertainty principle, picture trying to catch a super fast tiny fish in a big pond. The more certain you are about where the fish is, its position, the less sure you can be about how fast it's moving, its speed or momentum, and vice versa. If you know exactly how fast it's going, you can't be sure where it is. In quantum physics, this idea applies to particles. We can't know both exactly where a particle is and how fast it's moving at the same time. The more we try to pin down one piece of information, the fuzzier the other becomes. It's not because our tools aren't good enough, it's just how the universe works at the tiniest levels. This principle, discovered by Werner Heisenberg, is a fundamental part of quantum physics and affects how we understand and work with tiny particles. Superposition. Consider a coin in a closed box. While the box is closed, you can think of the coin as being both heads and tails at the same time. This is similar to superposition in quantum physics. In the quantum world, tiny particles can exist in multiple states at once until they're observed or measured. It's like they're exploring all possible options simultaneously. A famous thought experiment called Schrödinger's cat illustrates this. In this scenario, a cat in a closed box can be thought of as both alive and dead at the same time until we open the box to check. This principle is what makes quantum computers potentially powerful. While regular computer bits are either 0 or 1, quantum bits, qubits, can be 0 and 1 at the same time, allowing for many calculations to be done simultaneously. Quantum entanglement. Think of two dancers who always move in perfect sync, even if they're miles apart. That's a bit like quantum entanglement. In quantum physics, two or more particles can become entangled. This means that their properties are connected in such a way that you can't describe one particle without including the other, no matter how far apart they are. The wild part is that if you measure one entangled particle, you instantly know something about the other one, even if it's on the other side of the universe. Albert Einstein called this spooky action at a distance because it seemed to go against our usual ideas about how the world works. Entanglement is a key principle in quantum computing and quantum cryptography, where it's used to process information in new and powerful ways. Quantum tunneling. Let's roll a ball up a hill. Normally, if the ball doesn't have enough energy to reach the top, it rolls back down. But in the quantum world, sometimes the ball can magically appear on the other side of the hill, even if it didn't have enough energy to go over the top. This is quantum tunneling. It's as if the particle dug a tunnel through a barrier it shouldn't be able to cross. In reality, there's a small chance that the particle can suddenly appear on the other side of the barrier. This isn't just a cool trick, it's crucial for many things in nature. For example, it's how the sun produces energy through nuclear fusion and how some types of radioactive decay happen. We also use it in technology, like in scanning tunneling microscopes that can see individual atoms. Pauli exclusion principle. Picture a party where everyone must wear a unique outfit. No two people can have exactly the same clothes. This is similar to the Pauli exclusion principle, but for subatomic particles called fermions, which include electrons. In the quantum world, certain particles, fermions, can't be in the exact same state at the same time. For electrons in an atom, this means they can't have the same energy level, spin, and orbital. They have to be different in at least one way. This principle is super important. It's why atoms have different energy levels, why matter takes up space, and why the periodic table of elements works the way it does. Without it, all electrons would crowd into the lowest energy level of atoms, and the universe as we know it wouldn't exist. Quantum decoherence. A perfect sand mandala serves as a good analogy here. As long as it's isolated, it stays intact, but as soon as a breeze blows or someone touches it, the intricate pattern starts to break down. Quantum decoherence is a bit like this. Quantum systems, like our coin in superposition, are very fragile. When they interact with their environment, like being observed or bumping into other particles, they lose their quantumness. They go from being in multiple states at once to settling into a single definite state. This process explains why we don't see quantum effects in our everyday world. Big things are constantly interacting with their environment, so they quickly lose any quantum properties they might have had. Understanding and controlling decoherence is crucial for technologies like quantum computers, which need to maintain delicate quantum states to work properly. Quantum vacuum fluctuation. Visualize a fish tank that's never completely still. Even when there are no fish, tiny bubbles are always popping in and out of existence. The quantum vacuum is a bit like this. In classical physics, a vacuum is totally empty, but in quantum physics, the vacuum is actually full of energy and activity. Particles constantly pop into existence and then disappear again, all in the blink of an eye. These are called virtual particles. This isn't just a theory. We can actually measure the effects of these fluctuations. They cause things like the Casimir effect, where two very close parallel plates in a vacuum are pushed together by these quantum fluctuations. These vacuum fluctuations might even play a role in the expansion of the universe. They're a reminder that in quantum physics, even nothing is really something. Quantum computing, you're tasked with searching through a huge library for a specific book. A classical computer would check each book one by one. A quantum computer, on the other hand, could check all the books simultaneously. Quantum computers use the principles of superposition and entanglement to perform calculations, while classical computers use bits, 0 or 1. Quantum computers use qubits, which can be 0, 1, or both at the same time thanks to superposition. This allows quantum computers to perform certain calculations much faster than classical computers. They're especially good at things like searching databases, solving complex optimization problems, and simulating quantum systems, which is really hard for classical computers. While they're not going to replace your laptop anytime soon, quantum computers could revolutionize fields like cryptography, drug discovery, and material science.